Hi everyone, I'm Yating Huang, and today we're diving into the world of P, NP, and nitrogen monophosphide complete. Imagine P problems as sorting your daily emails. You know exactly how to get them organized quickly. NP problems are like solving a tricky Sudoku. Once it's done, checking the solution is a breeze, but finding it can take ages. NP complete problems are the ultimate brain teasers. If you discover a fast way to solve one, you've just unlocked a shortcut for all of them. We'll explore how these classes fit together, why nitrogen monophosphide complete is so famous, and what it would mean if P really did equal NP. Let's dive in. Now let's turn to one of the most famous nitrogen monophosphide complete problems, the traveling salesman problem. It asks, given a complete graph where each pair of cities I and j has a travel cost Cij, how do we find a single loop that visits every city exactly once, returns to its start, and has the smallest possible total cost? On the left, you'll see a toy example with 4 cities, A, B, C, and D, each connection labeled by its cost. On the right, there's a real-world map of Germany, tracing one such tour through major cities. Together, these visuals capture the heart of TSP, weighing all pairwise routes and selecting the visit order that minimizes overall travel expense. Building on our look at the traveling salesman problem, let's now explore Euler tours, a different but equally elegant challenge in graph theory. An Euler tour is a cycle that traverses every edge of a graph exactly once, even if that means revisiting some vertices. Imagine a one-pass street sweeper. It cleans every road without worrying about hitting the same intersection twice. This makes finding an Euler tour much simpler than solving TSP. You don't need to minimize distance or avoid repeats. On the left, you see a simple grid graph highlighted in red. The curved red line snakes through every edge exactly once, forming a perfect closed loop. On the right, there's an irregular 9-node network. The yellow arrows trace an Euler tour starting at node 1, then winding through nodes 2, 4, 5, 8, 9, 6, 7, looping back up through 6 and 3, and finally returning to node 1, again covering each link only once. These 2 examples illustrate a key theorem. If a graph is connected and every vertex has even degree, an Euler tour not only exists, but can also be found in linear time. Now that we've seen how Euler tours cover every edge exactly once, let's turn to Hamiltonian cycles. In an undirected graph, a Hamiltonian cycle is a simple closed path that visits every vertex exactly once. The central question is, given a graph G, does it contain such a cycle? It's like the Euler tour problem, but instead of covering edges, we must hit each vertex exactly once, which makes it significantly harder. In the example shown, the left diagram displays the original graph, and the right diagram uses bold lines to trace one valid Hamiltonian cycle that passes through every vertex without any repetition. Next, let's turn to another classic nitrogen monophosphide complete problem, the satisfiability, or SAT problem. Simply put, SAT asks whether we can make a given Boolean expression true by assigning each variable either true or false. Since each of the n variables has 2 possible values, that means 2 to the power of n assignments to check, a real exponential explosion. For example, consider the formula x or y or z, and not x or y and or don by and 20s and k's and the don my or not y and dot x or not y or not z, when I is shire. Here we have 5 clauses, each a disjunction of literals involving x, y, and z. To determine satisfiability, we must find at least one of the 2 to the power of 3 equals 8 possible truth assignments that makes every clause true. That combinatorial blow-up is exactly what makes SAT such a challenging problem. Now that we've seen how the number of possible assignments explodes, let's zoom in on a subtle yet crucial distinction. 2 SAT versus 3 SAT. In 2 SAT, every clause is limited to exactly 2 literals. For example, dot x or z, and not x or y, and x or not z, and z or not y, and not y or not z. By contrast, 3 SAT requires exactly 3 literals per clause. You might encounter something like dot x or not x or not X, and X or X or X, and not X or not X or not X or not X. At first glance, that extra literal seems minor, but its impact is huge. 2 SAT can be solved efficiently in polynomial time, whereas 3 SAT is nitrogen monophosphide complete and believed to have no similarly fast general solution. Building on our contrast between 2 SAT and 3 SAT, computer scientists have pinpointed a stubborn subset of problems for which no polynomial time solution is known. These hard problems seem to demand superpolynomial resources as their input grows, pushing beyond what we can handle efficiently. So here's the fundamental question in complexity theory. Is there a way to tell, up front, whether any given problem can be solved in polynomial time? Cracking that question would transform how we classify computational tasks and guide exactly where to focus our algorithmic efforts. Building on that, let's look at decision problems, those whose answer is simply yes or no. 2 classic examples are the Euler-Tour problem and the Hamiltonian cycle problem. On the left, you see a square subdivided into 4 regions, with its vertices labeled A through K. The red curve traces a closed path that uses every edge exactly once and returns to its starting point. That's an Euler-Tour. In the center, there is a 5-pointed, star-shaped graph with an inner pentagon. And on the right, the same graph is shown with a bold cycle that visits each vertex exactly once. That's a Hamiltonian cycle. In both cases, the fundamental question is, does such a tour or cycle exist? Now that we've explored decision problems, let's turn to optimization problems. Here, we're not just asking, does a solution exist, but what's the best solution we can find? For example, in the shortest path problem, we look for the minimum distance route from a starting node S to every other vertex. On the left, you see a directed graph with node S and 4 other vertices, U, V, X, and Y, connected by weighted edges, some even carrying negative values, illustrating the challenge of finding shortest paths under varied costs. On the right is a complete graph of 4 cities, A, B, C, and D, with every pair linked by a distance label, representing all possible tours the salesman could take. In the traveling salesman problem, our goal is to identify the single shortest tour that visits each city exactly once. Building on that foundation, let's examine how an optimization problem pairs with its decision counterpart. In the optimization version, you're handed a directed graph plus 2 vertices, U and V, and asked to find the shortest path between them. The decision version streamlines this. You still use the same graph and the same start and end points, but you're also given an integer k, and your only task is to answer yes or no. In other words, is there a path from U2 versus whose length is at most k? This transformation from find the best solution to verify a solution meets a threshold is a key technique in complexity theory. Continuing from our last slide, this one zeroes in on how an optimization problem can be reduced to its decision problem sibling. In a nutshell, if you can solve the full optimization task, you instantly gain the ability to answer the simpler yes or no question. Picture a directed graph with 2 vertices, U and V, plus a distance threshold k. The decision problem simply asks, is there a path from U2 versus whose length is at most k? To tackle it, just run your favorite shortest path algorithm, say Bellman-Ford, to compute the minimum distance between U and versus. Then check, is that distance no greater than k? If yes, answer yes. Otherwise, answer no. It's that straightforward, and it shows why having an optimization routine on hand makes decision versions a breeze. Building on our earlier discussion, let's highlight a simple but powerful point. Whenever the decision version of a problem is hard, its optimization counterpart can't be any easier. In fact, by rooting our hardness proofs in the decision version, we immediately guarantee that the full optimization problem is intractable. The diagram makes this crystal clear. The decision task sits inside the broader optimization task. So once you prove the decision case is hard, you've shown the entire problem is hard. Now that we've seen how proving hardness for decision problems also seals the fate of their optimization counterparts, Let's turn to measuring algorithmic efficiency with Big O notation. Big O captures an algorithm's worst-case running time by stripping away constant factors and low-order terms so only the dominant term remains. When that term is a polynomial and the input size n, we call the algorithm polynomial time. Think constant time O1, linear or n log n time, quadratic On squared, or cubic On cubed. By contrast, exponential time algorithms skyrocket in cost, with bounds like O2 to the power of n, On to the power of n, or even factorial time On, which become impractical almost immediately as n grows. Building on our discussion of polynomial time algorithms, we now define P as the class of decision problems that a deterministic Turing machine can solve in polynomial time. That is, there exists an algorithm whose running time is bounded by some polynomial function of the input size. A classic example in P is the Euler-Tour problem. Given a graph, decide whether there's a cycle that traverses each edge exactly once. You're allowed to revisit vertices. In the graph shown, with vertices A, B, C, D, and 7 numbered edges, you can indeed start at one vertex, follow a route that covers every edge exactly once, and return to your starting point. This concrete example shows how the Euler-Tour problem admits a polynomial time solution. Now that we've defined P as the class of problems solvable in polynomial time, let's explore some classic members of this family. Longest common subsequence, which finds the maximal matching sequence between two strings. Shortest path, which determines the least cost route in a graph. Minimum spanning tree, which connects all vertices with the minimal total edge weight. Euler-Tour, which visits every edge exactly once. Network flow, which maximizes throughput through a capacitated network. Together, these examples show just how broad and powerful Class P is, covering everything from string processing to graph theory and optimization. Now that we've seen a range of problems in P, those solvable in polynomial time, let's turn our attention to classic decision problems for which no such algorithms are known. First up is the Hamiltonian cycle problem, which asks whether a given graph contains a cycle that visits each vertex exactly once. Then there's the traveling salesman problem, where we look for the shortest possible tour through a set of cities. And of course, the SAT problem. Given a Boolean formula, can we find an assignment of truth values that makes it true? As far as we know, none of these three problems lie in P, and in fact, countless other problems seem to resist efficient solutions as well. So how can we systematically classify and compare problems that fall beyond P? Stay tuned, because that's exactly what we'll tackle next. To answer that question, let's first define the two foundational complexity classes, NP and PNP, short for non-deterministic polynomial time, consists of all decision problems that a non-deterministic Turing machine can solve in a number of steps bounded by a polynomial in the input size. In contrast, P is the class of decision problems that a deterministic Turing machine can solve in polynomial time. The key takeaway here is the difference between non-deterministic versus deterministic computation and their respective polynomial time limits. Building on our definition of NP, let's dive into non-determinism. A non-deterministic Turing machine, or NTM, behaves like an idealized parallel computer with infinitely many processors and unlimited bandwidth. Imagine each processor taking a different candidate solution and checking it at the same time. If any one of them finds a yes answer, the machine accepts immediately. On the bottom, you'll see two diagrams illustrating this on a graph search problem. In the left picture, every possible path is explored in parallel. In the right picture, one particular path is highlighted in bold, showing the successful route that our NTM would instantly discover. Building on that idea, let's introduce non-determinism in computation. Informally, you can think of a non-deterministic Turing machine as a parallel computer with infinitely many processors and unlimited bandwidth. Each processor explores a different candidate solution at the same time, checking it independently. The moment any one of those processors finds a valid yes answer, the machine as a whole accepts. This concept gives rise to the complexity class NP, which stands for non-deterministic polynomial time. NP is the set of decision problems for which, whenever the answer is yes, there exists a certificate or proposed solution that can be verified in polynomial time on a deterministic machine. In other words, Searching for a solution might be hard, but once you have one, checking it is efficiently doable. Building on our discussion of NP, let's look at the satisfiability, or SAT, problem. SAT asks whether there exists an assignment of true or false values to variables that makes a given Boolean formula evaluate to true. Formally, SAT sits squarely in NP. If someone hands us a candidate assignment, we can plug in the values and check each clause in polynomial time on a deterministic machine. For example, consider this formula composed of 5 clauses, x or y or z, during acidi, and to not x or y, and of x or not z, deriving not for not y, and of x or not y or not z. Verifying a proposed solution simply means evaluating each of these disjunctions under the assignment and confirming they all turn out true. That straightforward verification process is exactly what places SAT in NP, even though finding a satisfying assignment from scratch can be notoriously challenging. Just as SAT asks whether we can efficiently verify a satisfying assignment, the graph coloring problem asks us to assign one of k colors to each vertex of a given graph, so that no 2 adjacent vertices share the same color. In other words, we're looking for a valid coloring using exactly k colors, and a central question is whether deciding k colorability belongs to the class NP. On the left, you see a 5-vertex graph and its corresponding internal star, successfully colored with 3 colors so that every connected pair ends up with different colors. On the right, there's a partially filled Sudoku grid, which can be modeled as a graph coloring instance. Each cell becomes a vertex, edges connect cells in the same row, column, or block, and the digits play the role of colors. This example highlights both the abstract definition and a concrete application of graph coloring. Building on our discussion of graph coloring, we now ask, is the Hamiltonian cycle problem in NP? To illustrate, on the left you see a 5-layered pentagonal graph, with every vertex woven into a web of edges. On the right, one possible Hamiltonian cycle is traced in bold, visiting each vertex exactly once before returning to its starting point. The beauty of this example is that, given a proposed cycle, we can verify in polynomial time that it indeed includes every vertex without repetition and follows only valid edges. That efficient, step-by-step check is precisely what places the Hamiltonian cycle problem squarely in NP. Now let's turn our attention to an Euler tour example on a simple graph. This graph is a square divided into 4 equal smaller squares by a vertical and a horizontal segment. Its 10 vertices are labeled A, B, C along the top edge, K and H at the upper left and lower left corners, E and C at the lower right and upper right corners, J and D at the midpoints of the left and right sides, and G at the center where the 2 dividing lines cross. All the edges of the large square, plus the 2 dividing segments, form the graph's edge set. The red line traces a path that starts at J, follows the left border up to A, then moves across to B, down through the center to F, along the bottom to E, up to D, and finally back through the central segment to G, covering every edge exactly once before it returns to its starting point. That's an Euler tour. The key takeaway is that, given such a candidate tour, we can verify in polynomial time that every edge appears exactly once, and that each pair of consecutive edges shares a common vertex. That efficient check shows the Euler tour problem belongs squarely in NP. Building on that Euler tour example, let's recap P versus NP. First, P is the set of decision problems we can solve in polynomial time. NP, on the other hand, is the set of decision problems for which, given a proposed yes answer, we can check its correctness in polynomial time. Because any problem we can solve quickly, we can also verify quickly, every problem in P falls inside NP. That relationship is pictured by the smaller P circle nestled inside the larger NP oval. And remember, NP doesn't automatically mean a problem is hard. Some NP problems are easy, some may be tough, and we still don't know whether P equals NP. Now that we've laid the groundwork, this slide throws down the gauntlet. P versus NP, the single biggest unsolved problem in computer science. Crack it. Prove or disprove that P equals nitrogen monophosphide, and you'll almost certainly walk away with the Turing Award and at least $1 million. After pulling off a feat like that, you can kick back and enjoy life, just like the person relaxing on the beach in our image. Now that we've seen just how big a deal P versus NP really is, and why solving it could earn you a Turing Award and a beachside vacation, let's dig into the heart of the matter. Is P equal to NP? Unfortunately, despite decades of research, we still don't have polynomial time algorithms for many classic challenges: the Hamiltonian cycle problem, the traveling salesman problem, the click problem, vertex cover, and several others. This persistent gap suggests that some problems in NP may indeed be inherently harder than others. We'll revisit this hierarchy of difficulty later in the course. Building on our central question of P versus NP, let's now distinguish these two fundamental complexity classes. P includes all decision problems that can be solved in polynomial time, while NP contains those problems for which a proposed yes answer can be verified in polynomial time. It's crucial to note that NP doesn't automatically mean a problem is hard. It simply refers to verification rather than solution. As the diagram below shows, every problem in P fits inside NP, and the big mystery remains: are P and NP really the same? That question still stands as one of computer science's greatest open problems. To bridge the gap between a tough problem A and a more manageable problem B, we use polynomial time reductions. Here's how it works. Given an input alpha for problem A, we first run a reduction algorithm in polynomial time that converts alpha into a new instance beta of problem B. Next, we feed beta into our known polynomial time decision procedure for B. Finally, we take B's yes or no result and map it back to give the correct answer for A. In the diagram, you can see alpha entering the reduction box, emerging as beta, passing through B's algorithm, and then having its yes-no output translated back into A's answer, all while staying within polynomial. Building on what we just saw, let's explore a concrete example of problem reduction. We start with problem P, the single-source shortest path task. Given one source vertex S, find the shortest distances from S to every other vertex in the graph. Next is problem Q, the all pairs shortest path task, where we want the shortest distance between every possible pair of vertices. The key insight is that if you can solve Q, you automatically solve P. Just pick your source vertex and read off its distances from the full all pairs solution. In other words, Q is at least as hard as P, since any algorithm for Q can be used to handle the single source case as well. We line up the first points in order, and then look for a longest increasing subsequence among their matching second points. This way, we pick as many non-crossing pairs as possible. In our toy example, 8 red points along the top are numbered 1 through 8, each connected to a point below. Reading the bottom labels in the order of the top labels gives us the sequence: 1, 5, 6, 2, 3, 4, 7, 8. Mive. To avoid crossings, any valid chain must pick numbers in ascending order. The longest increasing subsequence of that list is 1, 2, 3, 4, 7, 8. So we can select 6 non-crossing pairs. That sequence, 1, 2, 3, 4, 7, 8, is our optimal solution. Now that we've seen how finding a longest increasing subsequence helps us pick non-crossing pairs, let's turn to another powerful idea: reduction, a fundamental technique for comparing problem difficulty. At its core, reduction means taking the input of one problem, which we'll call P, and converting it into an instance of another problem, Q. By doing this, we can solve P indirectly. First solve Q, then map that solution back to P. Here's the key takeaway. If we can reduce P to Q, then P is no harder to solve than Q. In other words, Q must be at least as difficult as P. This comparison underpins many proofs of computational hardness. By showing that a known hard problem reduces to a new problem, we establish that the new problem is at least as challenging. Building on our discussion of reductions, let's turn to 2 key complexity classes: NP-hard and NP-complete. First, we call a problem A nitrogen monophosphide hard if every problem in NP can be reduced to A in polynomial time. Put simply, NP hard problems are at least as tough as the hardest problems in NP, Next, we define nitrogen monophosphide complete problems. A problem B is nitrogen monophosphide complete if it satisfies two conditions. It's nitrogen monophosphide hard, and it also belongs to NP. In essence, NP complete problems are the ultimate challenges within NP. They can be verified quickly and are as difficult as any other NP problem. Building on our previous definitions, this slide shows why nitrogen monophosphide complete problems are truly the hardest in NP. Imagine if you could solve any nitrogen monophosphide complete problem in polynomial time. Suddenly, every problem in NP would also become solvable in polynomial time. In other words, you'd have proven that P equals NP. Even an astronomically high-degree polynomial algorithm for the Hamiltonian cycle problem, say ON(100,000), would be enough to establish P equals NP. That single breakthrough would instantly settle one of computer science's biggest open questions and, as the slide winks, make you rich and famous. Now let's build on that idea by introducing two central concepts in computational complexity. First, a problem P is called nitrogen monophosphide hard if every problem in NP can be transformed or reduced to P in polynomial time. In other words, P is at least as tough as the hardest problems in NP. Second, a problem B is nitrogen monophosphide complete exactly when it meets two conditions. It's nitrogen monophosphide hard, and it itself belongs to NP. And here's the big takeaway. Hardness is preserved under polynomial time reductions. So if you can reduce a known nitrogen monophosphide hard or NP complete problem B to another problem Q, then Q inherits nitrogen monophosphide hardness as well. Building on that foundation, let's talk about Stephen Arthur Cook, born in 1939. In 1971, he revolutionized modern complexity theory by formalizing nitrogen monophosphide completeness. In his landmark paper, he proved that the circuit satisfiability problem is nitrogen monophosphide complete, the very first problem of its kind. This breakthrough went on to earn him the Turing Award in 1982. But believe it or not, early in his career, UC Berkeley's math department denied him tenure. Undeterred, Cook soon joined the University of Toronto, where he continued to shape our understanding of computational complexity. Building on Cook's foundational insights, we now turn to Richard Karp, a pioneering computer scientist born in 1935 who has spent his career as a professor at UC Berkeley. In 1972, Karp published his landmark paper, Reducibility Among Combinatorial Problems, in which he identified and formally proved 21 core problems as nitrogen monophosphide complete, work that truly launched the field of computational complexity as we know it today. Decades later, speaking at the 30th anniversary of Berkeley's EECS department, Karp wryly remarked that it was, to our everlasting shame, the math department had refused him tenure, an ironic footnote to a legacy that forever reshaped how we understand hard problems. Building on Karp's groundbreaking work defining nitrogen monophosphide completeness, we start with circuit SAT, the original nitrogen monophosphide complete problem. From there, we reduce to the classic Boolean formula problem SAT, then narrow it down to its restricted form, 3CNF-SAT. At that point, the reductions split into two main branches. On one side, 3CNF-SAT maps to click-in graphs, then to vertex cover, then to ham cycle, and finally, to the traveling salesman problem. On the other side, 3CNF-SAT goes directly to the numerical subset sum problem. Every nitrogen monophosphide completeness proof in these sections follows one of these arrows, tracing back ultimately to circuit SAT. Now that we have this roadmap, let's dive into each reduction in detail. With this roadmap in place, let's zoom out and see what nitrogen monophosphide complete problems are really all about. These decision problems form a special class whose exact complexity remains unresolved. To date, no polynomial time algorithm is known for any of them. We use nitrogen monophosphide completeness as a kind of yardstick by reducing a known nitrogen monophosphide complete problem to a new one. We prove the newcomer is at least as hard. And while the P versus NP question is still wide open, any problem that earns the nitrogen monophosphide complete label is widely believed to be intractable in the general case. As a result, once a problem carries that designation, most efforts shift away from searching for an exact polynomial time solution and move toward approximation algorithms, clever heuristics, or restricted variants. Building on that definition, to prove that a problem P is nitrogen monophosphide complete, we follow two key steps. First, we show P lies in NP, meaning any yes answer can be verified in polynomial time. Second, we prove nitrogen monophosphide hardness by reducing a known nitrogen monophosphide complete problem Q to P. Concretely, we pick a well-studied nitrogen monophosphide complete Q and describe a polynomial time transformation that turns any instance of Q into an instance of P. We then demonstrate that Q yields yes exactly when the transformed P instance does, and we verify the whole mapping runs in polynomial time. Once both membership in NP and this reduction are established, P is nitrogen monophosphide complete. Now, building on our nitrogen monophosphide completeness framework, we start at the very top with circuit SAT, the original nitrogen monophosphide complete problem. From there, we reduce circuit SAT to the general SAT problem, and then to the more restricted 3CNFSAT. At that point, the reduction graph splits in two directions. One path goes to click, the other to subset sum. Let's zoom in on the click branch. From click, we next reduce to vertex cover, then to ham cycle, and finally to the traveling salesman problem. The highlighted portion here shows our last step, proving TSP is nitrogen monophosphide, complete by a reduction from the Hamiltonian cycle problem. Remember, every one of these nitrogen monophosphide completeness proofs ultimately traces all the way back to circuit SAT. Now that we've just seen how Hamiltonian cycles reduce to the traveling salesman problem, let's dive into TSP itself. At its core, TSP is defined on a complete graph where every pair of cities I and J has an associated travel cost Cij. In the optimization version, we're looking for a tour that starts at one city, visits each of the n cities exactly once, returns to the starting point, and incurs the smallest possible total cost. In the decision version, we simply ask, is there a tour whose total cost does not exceed a given threshold, K? To make this concrete, imagine a tiny four-city example with nodes labeled U, V, W, and X. The cost from U to versus is 4, from V to W is 2, from W to X is 5, from X back to U is 3, and the two diagonals, U to W and V to X, each cost 1. Even in this small setup, the core challenge jumps out. How do you pick the right sequence of cities to minimize the total travel expense? Building on our previous discussion, let's now formalize the decision version of the traveling salesman problem, or TSP. We start with an input, G, C, K, where G equals V, E is a complete graph, and C assigns a non-negative cost to each edge. The question we ask is simple. Does there exist a tour that visits every city exactly once, returns to the starting point, and has total cost less than K? In the diagram, we see a four-city example with vertices labeled U, V, W, and X. Every pair of cities is connected by an edge with these weights. UV costs 4, UX costs 3, V-2 costs 2, XW costs 5. The diagonals U-W and VX each cost 1. Our goal is to find a Hamiltonian cycle, that is, a route touching each city exactly once and looping back to the start, such that the sum of these edge weights remains below the threshold K. Building on our previous discussion of the traveling salesman problem, today we introduce the Hamiltonian cycle problem. We start by assuming that deciding whether a given graph contains a simple cycle visiting every vertex exactly once is nitrogen monophosphide complete. On the left, you'll see a complex 5-layered network of nodes and edges. On the right, the same network is shown again, with one valid Hamiltonian cycle highlighted in bold and all other edges lightly dotted. This example illustrates both the challenge of finding such a cycle and why the Hamiltonian cycle problem sits at the heart of NP completeness. Building on our discussion of Hamiltonian cycles, let's now show that the traveling salesman problem lies in NP by demonstrating how easily a candidate tour can be checked. Imagine a simple 4-vertex graph with nodes U, V, X, and W. The edges carry weights as follows. UV is 4, VW is 2, WX is 5, XU is 3, and the two diagonals UW and VX each weigh 1. Suppose someone proposes the tour U right pointing arrow W right pointing arrow V right pointing arrow X right pointing arrow U. To verify it, you simply visit each vertex once, sum the edge weights, 1 plus 2 plus 4 plus 3, and confirm whether that total meets your cost bound. Because you only need a single pass through the tour and one addition per edge, this check runs in linear time. This simple example illustrates why any proposed TSP tour can be verified in polynomial time, establishing that TSP is in NP. Building on our previous discussion, this slide lays out the two key steps for proving that the traveling salesman problem is nitrogen monophosphide complete. First, we reaffirm that TSP belongs to NP by observing that any proposed tour can indeed be checked in polynomial time. Just a single pass through the tour and a few additions. Second, we reduce the undirected Hamiltonian cycle problem to TSP. In practice, we take any graph from the Hamiltonian cycle problem and construct a corresponding TSP instance so that a tour of length, at most some bound, exists exactly when the original graph has a Hamiltonian cycle. In other words, if we had a TSP solver in hand, we could feed it these transformed instances and thereby solve Hamiltonian cycle as well. The final piece is to show how to carry out this transformation for every possible input and to ensure that it, too, runs in polynomial time. Next, we'll dive into the specifics of how that reduction is carried out. So, let's walk through the reduction from the Hamiltonian cycle problem to TSP step by step. Start with your original graph G on vertex set V and build a new complete graph G' over the same vertices. For every edge that already exists in G, assign it weight 0 in G'. For every other pair of vertices, insert an edge of weight 1. Now pose the TSP decision question. Is there a tour in G whose total weight is strictly less than 1? Because any tour with weight under 1 can only use 0 weight edges, it must follow a cycle in the original graph G, meaning it's a Hamiltonian cycle in G. And conversely, any Hamiltonian cycle in G becomes a 0 weight tour in G. This 0 weight criterion gives us an exact polynomial time reduction from Hamiltonian cycle to TSP. Next, we'll verify that this construction indeed runs in polynomial time and wrap up our nitrogen monophosphide completeness proof. Building on that weight 0 idea, here's how we reduce Hamiltonian cycle to TSP in polynomial time. First, take your unweighted graph G and form a complete graph G' on the same set of vertices. For each edge that was already in G, assign weight 0 in G. For every other pair of vertices, assign weight 1. In our diagram, gray edges are the original 0 weight ones, and orange edges are the new weight 1 connections. Notice that any tour in G with total length 0 must use only 0 weight edges, so it corresponds exactly to a Hamiltonian cycle in G. Conversely, any Hamiltonian cycle in G produces a 0-cost tour in G. Because this construction runs in polynomial time, it proves that solving TSP is at least as hard as finding a Hamiltonian cycle. Now that we've constructed G, let's prove that finding a Hamiltonian cycle in G is exactly the same as finding a 0-weight tour in G. In the illustration, our original graph G sits on the left. On the right is G, the complete graph on the same vertices, where every edge that existed in G carries weight 0, and every new edge carries weight 1. First, if G has a Hamiltonian cycle, then those edges all exist in G as WEIGHT 0 edges. So you can retrace the exact same cycle in G using only zeros, giving you a tour of total weight 0. Second, if G admits a tour of total weight 0, it can't include any weight 1 edges, otherwise the sum would exceed 0. That means it uses only 0 weight edges, and by construction those edges correspond to edges in G. Hence that tour is a Hamiltonian cycle in G. With both directions established, we've shown our reduction is correct. So, in summary, We began by showing that the traveling salesman problem lies in NP. Then we built a polynomial time reduction from the Hamiltonian cycle problem to TSP, meaning any algorithm that solves TSP can also decide Hamiltonian cycles. Putting those two results together, we conclude that TSP is nitrogen monophosphide complete. Building on our last conclusion, let's compare the Hamiltonian cycle problem in directed versus undirected graphs. At the top, we remind you that finding a Hamiltonian cycle, one that visits every vertex exactly once, is already nitrogen monophosphide, complete when edges have a prescribed direction. So, does dropping the arrows make the problem any easier? On the left, you see a small directed graph with arrows indicating allowed moves. On the right, the same underlying connections appear without arrows. Despite this seemingly simpler setup, the undirected version remains just as hard. It, too, is nitrogen monophosphide complete. Building on our previous result, we'll now show that the undirected Hamiltonian cycle problem is in NP. Imagine we're handed a candidate sequence listing all vertices. First, we check that each vertex appears exactly once. Next, we verify the sequence actually closes by repeating the starting vertex at the end. Finally, we confirm that every consecutive pair of vertices in this list is connected by an edge, ensuring a valid cycle. Since each of these checks runs in polynomial time, the undirected Hamiltonian cycle problem indeed belongs to NP. Building on our previous proof, this slide presents the classic reduction from the directed Hamiltonian cycle problem to its undirected counterpart. We start with a directed graph G equals VE and construct an undirected graph G equals VE in two clear steps. First, for each vertex V in V, we introduce a vertex gadget by creating three new vertices, V, V squared, and V cubed in V iris, then adding undirected edges, V, V squared, and V squared, V cubed. This gadget ensures that any Hamiltonian cycle must enter at verses, pass through V squared, and exit at V cubed. Next, for every directed edge, vo nalu W in E, we connect V's gadget to W's gadget by adding a single undirected edge between V cubed and W in E. These links exactly mimic the original direction of edges in G. Thanks to this construction, any directed Hamiltonian cycle in G corresponds 1-for-1 with an undirected Hamiltonian cycle in G, and the reverse is true as well. The small example at the bottom illustrates this. On the left, you see a 3-vertex directed cycle. On the right, its transformed undirected gadget graph. Can we perform this transformation in polynomial time? We'll answer that question on the next slide. Building on the previous slide, this one shows a standard reduction that turns any directed graph G into an undirected graph G', so that G has a directed Hamiltonian cycle exactly when G' has an undirected one. The construction unfolds in two key steps. 1. For each vertex V in G, create 3 vertices, V, V squared, and V cubed in G, and link them in a small path, V, V squared, and V squared minus V cubed. 2. For each directed edge, V right pointing arrow W in G, add a single undirected edge in G from V cubed to W. Because any Hamiltonian cycle in G must enter at verses, pass through V squared, then leave from V cubed, it inherently preserves the original direction from V to W. On the right, you see a concrete example. A 3-node directed cycle is blown up into 9 vertices, with the orange loop tracing a valid Hamiltonian cycle in G that mirrors the original directed cycle. Building on our last slide, let's see why this reduction from directed to undirected Hamiltonian cycle actually works. On the left, you have the original directed graph G, 3 yellow vertices linked by arrows that form a directed cycle. On the right is the constructed undirected graph G. Here, each vertex from G is blown up into a little gadget of 3 nodes, alternately orange and yellow, and every directed arc in G becomes a corresponding path of undirected edges in G. Now, if G has a directed Hamiltonian cycle, you can follow that cycle and, at each step, traverse the matching gadget path in G. Doing so visits every node of G exactly once and brings you back to the start. In other words, Any directed Hamiltonian cycle in G maps directly to an undirected Hamiltonian cycle in G. That's the if direction of our reduction. Building on our previous reduction, we now translate any directed Hamiltonian cycle instance G into an undirected graph G graph so that G has a directed cycle exactly when G has an undirected one. First, for each vertex V in G, we replace it with a 3-node gadget, an in node, a mid node, and an out node linked in a simple path. Then, for every directed edge U right pointing arrow V in G, we insert an undirected edge from U underscore out to V underscore in G. On the left is the original G, a simple directed 3-cycle. On the right, you see the constructed G with 9 nodes in total, arranged as 3 gadgets, yellow mid-nodes flanked by orange in and out nodes, plus the inter-gadget connections mirroring the original arcs. The bold orange edges trace one undirected Hamiltonian cycle in G. You enter each gadget through its in node, visit the mid node, exit via the out node, then hop along the connecting edge to the next gadget. Because this construction works both ways, G has a Hamiltonian cycle if and only if the original directed graph G does. Conversely, suppose our undirected graph G admits a Hamiltonian cycle. Then the original directed graph G must admit one too. Remember that each vertex V in G was replaced by a 3-node gadget in G, an in node, a mid node, and an out node. Because the mid node has exactly 2 connections, one to the in node and one to the out node, any cycle in G is forced to pass through the gadget in order, either in right pointing arrow, mid right pointing arrow out, or out right pointing arrow, mid right pointing arrow in. Whenever the cycle uses an edge from the out node of gadget U to the in node of gadget V, that edge mirrors the directed arc UV in the original graph. By chaining these gadget-to-gadget moves, you recover a directed Hamiltonian cycle in G. In this way, any cycle in G translates directly into a cycle in G. Building on that, if our reduced graph GB admits an undirected Hamiltonian cycle, we can reconstruct a directed cycle in the original graph G simply by tracing the same sequence of vertices. The reduction was carefully crafted so that every undirected edge in G corresponds to exactly one directed arc in G. For example, take the cycle 1 right pointing arrow, 2 right pointing arrow 3 right pointing arrow 1. In G, the connections between vertices 1, 2, and 3 form an undirected triangle, but because of how we built those edges, moving from 1 to 2 must use the 1 right pointing arrow 2 arc in G, from 2 to 3 the 2 right pointing arrow 3 arc, and from 3 back to 1 the 3 right pointing arrow 1 arc. The picture on the left illustrates the undirected triangle in G, and the one on the right shows the resulting directed triangle in G. In this way, any undirected Hamiltonian tour in G immediately yields a valid directed Hamiltonian cycle in G. Now that we've seen how a Hamiltonian cycle reduction works, let's step back and highlight 2 key observations about NP problems. First, NP-complete problems are those for which no polynomial time solution is known. In practice, they seem to demand exponential time. To prove a new problem is nitrogen monophosphide complete, you pick a problem already known to be nitrogen monophosphide complete, craft a reduction to your problem, and then rigorously show that this reduction holds. Second, there's an entire class of decision problems that live in NP but are neither NP nor proven nitrogen monophosphide complete. These in-between problems are especially intriguing. If you could show even one of them is nitrogen monophosphide complete, you'd resolve once and for all that P does not equal NP by proving no polynomial time algorithm exists for it. The diagram here illustrates NP as the universe of decision problems, with P as a small subset and NP complete as another subset. Notice the unclassified region between them. Those are the mysteries still waiting to be solved. Building on that idea, let's consider graph isomorphism. It asks whether 2 graphs are the same up to a relabeling of vertices. Here you see the same 8-vertex, 12-edge structure drawn 2 ways. On the left, it's laid out as a complete bipartite pattern. 4 nodes on the left, 4 on the right, all cross-connected. On the right, it's arranged like a cube, with an outer square connected to an inner square. Matching colors highlight the one-to-one correspondence between vertices. Despite this simple statement, and this crystal-clear example, no polynomial time algorithm is known, nor has the problem been proved nitrogen monophosphide complete. Graph isomorphism sits squarely in that intriguing gray area between P and NP complete. Now let's turn to another classic combinatorial puzzle, the pancake flipping problem. A messy chef serves up a stack of pancakes in random sizes, and the waiter's job is to sort them so the smallest pancake ends up on top and the largest on the bottom. He does this by sliding a spatula under the top K pancakes and flipping the entire block, reversing their order each time. The real challenge? Finding the sequence of flips that achieves a fully sorted stack in as few moves as possible. And here's the kicker. By 2011, it was proven nitrogen monophosphide. Hard to determine that minimum number of flips for an arbitrary stack. Building on that nitrogen monophosphide hardness insight, let's dive into the classic pancake flipping problem. You have a stack of N pancakes in random order, and your only move is a prefix flip. You slide a spatula under the top K pancakes and flip them as a block. The goal? Sort the stack by size, smallest on top and largest on bottom, using the fewest flips possible. After decades of study, we still don't know whether there's a polynomial time algorithm for this task. However, there's some good news. In ESA 2005, researchers presented a simple two-approximation algorithm for sorting by prefix reversals, which guarantees a solution within twice the minimum number of flips. Next, we revisit the pancake flipping problem, sorting a stack of differently sized pancakes by repeatedly flipping the top K pancakes. In 1979, Bill Gates and Christos Papadimitriou proved that any stack of N pancakes can be sorted in, at most, 5/3 N plus 1 flips. This result gives us a clear worst-case guarantee for the number of prefix reversals needed. And to keep things light, you'll also see a playful cartoon of Gates and Papadimitriou tackling their own pancake stacks. Building on that pancake flipping result, let's zoom in on one of its co-authors, Christos Papadimitriou. He's a professor in the computer science department at UC Berkeley, and one of the world's foremost experts in computational complexity theory. On the left, you'll see his portrait. On the right, the cover of his seminal book, Computational Complexity, which has reshaped how researchers understand the limits of efficient computation. His work continues to inform algorithm design, define complexity classes, and drive advances across theoretical computer science. Interestingly, long before Microsoft existed, Bill Gates was already delving into serious math. As an undergraduate at Harvard, he teamed up with Christos Papadimitriou to tackle the pancake sorting problem. Their joint paper, Bounds for Sorting by Prefix Reversal, appeared in Discrete Mathematics in 1979, and remarkably, it remains the only academic paper Gates ever published. Not long after, he left Harvard to found Microsoft. Now, as we conclude our discussion, you'll see that hundreds of decision problems have been classified as nitrogen monophosphide complete. Classic examples include finding a Hamiltonian path or cycle, determining a minimum vertex cover, and tackling the set cover problem. For a detailed list of these nitrogen monophosphide complete challenges, be sure to check out the comprehensive catalog available at the link provided. And remember, while some reductions require deep insight, many turn out to be surprisingly straightforward once you zero in on the core idea.